So our first example of two-dimensional motion, we've been given a particle's trajectory described by this function. Remember S represents position. When we talk about the word trajectory, we typically mean the path the particle takes. So this function is describing where the particle is at any given moment in time. It tells us that S is measured in meters, meaning the 1/2, the 2, the 1/2, the 2 need to have units such that when we plug in time, the whole term comes out in meters. Now, remember, we can say that the position of an object at any given moment in time can be written as some sort of x component plus some sort of y component. When we look at this function, I see I hat here, so I can say that the x component of this position, this particle, where it is in the x direction, at any given moment in time, is described by that 1/2 t cubed minus 2t squared. Everything in parentheses in front of the I hat. The j hat, I can say that the y position of this particle at any moment in time is described as the 1/2 t squared minus 2t. Now, you can leave it in the vector form, that's totally fine. Or you can pull out like I just did and say, all right, I have x, I have y. Either way, I know to get to velocity, I need to take the derivative. But when I take the derivative of this portion, I get specifically the x component of velocity. So let's see, 3/2 t squared minus 4t. That will be the function that describes the x component of the velocity. When I take the derivative of this y position, let's see, 2 times 1/2, I'll just write it this way for just a minute. So t minus 2. So essentially, we could say that the velocity of this particle at any moment in time is this x component of velocity, I hat, plus this y component of velocity, j hat. And it's fine, like I mentioned, you can leave, and just knowing that, you can take the derivative and get to this form right away. So the question overall is asking us for the magnitude and direction of the velocity at time equals 3 seconds. So we want to plug in that time, our x component of velocity, 3 squared. I'm getting 1.5. This will be in meters per second since they told us that the position was measured in meters. Plugging in over here, the y component ends up being 1 meter per second. And we would find the same thing if we plugged in over here. But we're not done because this is giving us specifically the component. What this means is the velocity has a component in the positive x direction of 1.5 meter per second, and then a component in the y direction of 1 meter per second. Remember the terminology magnitude and direction always refer to the length of the hypotenuse. So the magnitude of the velocity vector is the speed. So we want to know the length of the hypotenuse. Direction refers to an angle. So knowing these components, we can find the length of the hypotenuse using Pythagorean's theorem. So 1.5 squared plus 1 squared. And then square root of that. So 1.8. That's the magnitude, the speed. We can say that the tangent of theta is the opposite side, which is 1, over the adjacent side, that is 1.5. So when I take the inverse tangent of that, I get 34 degrees. So the magnitude and direction of the velocity at this time is 1.8 meters per second at 34 degrees. This is already measured relative to a positive x-axis going counterclockwise. So leaving it as 34 degrees is perfectly valid. We're in that first quadrant. So similar to the linear motion problems, if we're given a function describing position, velocity, or acceleration at any given moment in time, you'll typically be using the calculus relationships. So since this was position, that's why we took the derivative to get to the velocity. Had the problem asked for acceleration, we would have just taken the derivative again and then plugged in the time there. So given a function, use the calculus relationships.